Does anybody remember what the word rational means? Or what a rational number is? Maggie? Oh, that's sad. Thanks. What happened? That's weird. Maybe this guy's weird. I have no idea. This is where those are. Turn you on. I think I'm recording this. Okay, here we go. Okay, can anybody tell me what the word rational, or really what a rational number was? Jeremiah? Excellent. A number that can be placed in the form of a fraction. So what do you suppose a rational function is? Well, it's just a function with two functions within a fraction. So example, it looks like this, where you have f of x is equal to one function, we could call it p of x, divided by another function, q of x. It's just a fraction made up of functions. So we could even write that. What is a rational function? Dividing two functions. Because remember, a fraction is just dividing. Okay, we're going to start with the most basic rational function to try to help develop how do we graph and look at different aspects of other rational functions. So first of all, we're going to explore the end behavior for a rational function, so the end behavior, how the graph behaves at the end, by using the table with the most basic rational function, y equals 1 over x. So what I'd like you to do is you're going to plug this into your calculator, and then you're going to build your table. Now, I'm going to write down the commands you'll use on your calculator, just in case you are in a different spot than other people, you can look back at the screen. So after you enter this function into your calculator, y equals 1 over x, then you're going to press second window. What? Oh, yeah, it looks weird. So after you put that in, you're going to press second window. This is your table set option. And you can change the way that you look at your table. So if you look at like this table here, where does the table start at? The table starts at -3. So at table start, this would be the number that I would put in, -3, table start. And then what are these numbers changing by? 1 unit. So in my change table, so it'll say change table after we plug that in, you're going to put in the number 1 because you're going to change it by 1 unit. So what we want to do is we want to look at the end behavior of this graph and just see what's happening numerically inside of the table. So we're going to look at numbers with whole number values, we'll look at numbers with decimals, and then even smaller decimals, and see what is happening within this graph. So this is the table that you would have had after you changed your tables. Now we're going to start analyzing, well, what happened in the graph? And specifically, we know what the graph looked like because we graphed it on the calculator. We know that it had this shape going on and this shape going on. Oh, thanks. Thanks, guys. Forget I need to change functions. There we go. So we know that you had this graph and you have this shape happening and you have this shape happening. And the first thing that we are looking at is what's happening at the x value of 0. Why does it look funky? Why is it approaching these numbers, and what's happening to those numbers? So the first thing we're looking at is from the negative direction. So from like, that was -1, this is -2, this is -3. And the question asks, as x gets very, very close to 0 from the negative side, so this would be from the negative side, this would be the types of numbers that are getting very, very close to 0. So I'm just showing this is the side that we are referencing right now. What happens to the y values? So now take a look at the y values. What's happening there? They're getting bigger in negativity, right? They're getting larger and larger, more negative. We could say smaller because, yeah, they're getting smaller in value. But I kind of like seeing that they're more and more negative. More and more negative. So like in the table, we're seeing that those negative values are getting higher. Now let's see how that shows up on the graph. On the graph, that means that as the numbers are getting closer and closer and closer to 0, they're getting further and further and further negative in y value. Do you think they're ever going to actually touch 0? No. So that's just kind of a distinguishing feature of this graph. It's getting closer and closer and closer to 0. Now, as x gets very close to 0 from the positive side. So here's my positive numbers. It's getting closer and closer and closer to 0. So this would be my positive side. What's happening to the y values? So what's happening on the other side of the table? They're getting bigger. They're getting more positive. They're getting bigger. More positive, and I like that it's getting bigger. Technically, up here, we could say smaller, because higher negative values is smaller. So as x gets very close to 0 from the positive side, what's happening to the y values? They're getting bigger and bigger, more and more positive. More and more positive. They're getting bigger. Now let's see how that looks on the graph. On the graph, that means as the x's are getting closer and closer to 0 from the positive side, so they're moving this way, they're increasing, they're going to actually increase forever in value. Now, why is there an error when x is equal to 0? You can't, we can't have, if you have your function y equals 1 over 0, you cannot have a denominator equal to 0. Now, how does that error appear on the graph? So let's go back to the graph here. I'm going to look up here. There's where x is equal to 0. How does that appear on the graph? What's happening there? All the numbers are approaching that, right? There's no solution at 0. And do you guys see that it kind of looks like a vertical line, like all the numbers are approaching this vertical line? Wherever x is equal to 0 in the denominator, that's called a vertical asymptote. So how does the error appear on the graph? It appears in the form of a vertical asymptote. Vertical. And there's only one S in that. I definitely, when I was first teaching this, accidentally put 2 S's. That's not quite a math term. It's A-S-Y-M-P-T-O-T-E. So just so you don't make that same mistake as I did, and I was actually teaching. So, but the vertical asymptote, and then just so you know what's happening, all the y values are getting very close to it. All the y values get very close to, but never touch. But never touch that vertical asymptote. And you can see that just with the tables that you developed, that those y values get bigger and bigger or smaller and smaller, but they don't ever actually touch where x is equal to 0. Okay, so let's take that understanding to 2 new graphs. So for function f of x, where do you think the error will appear? Where, yes, at x equals 2. So when x is equal to 2, so if I sketch the graph, even before I use my graphing calculator, if I kind of just do an xy axis, based off of what we just learned, what do I know is going to happen at the x value of 2? It's going to be an asymptote, and specifically a vertical asymptote. So at x equals 2, I have this, you can just kind of create it as a dashed line. And now we know that right around that vertical asymptote, so everything close to it, like 1.999 and 2.00001, those numbers, wherever they lie, they're going to get really, really close to that asymptote. Now we're going to learn how in a moment. For right now, let's just use our graphing calculator to see what the shape of the graph appears. But you at least have one component of it down. So go back to your y equals, and let's graph this one, 2x plus 3 over x minus 2. And if I graph this, I can see my graph. It does do as I predicted. All of the numbers are getting closer and closer to 2. So specifically, I have this going on, Getting close. And notice this is just a sketch. I haven't asked for accuracy yet. And then everything's kind of moving up close that way, going in this way. Now, after you've seen what a vertical asymptote looks like on the graph, if you look at your graphing calculator, you might notice it looks like there's a horizontal asymptote here as well. It looks like there's a horizontal line of which all of these numbers are approaching. And you're right, there is a horizontal asymptote, and we'll learn where that comes from in a moment. But for right now, why don't you try the next example with your partner and see if you can figure out where the vertical asymptote will lie. Guys, here's what I saw. I saw different groups. Most everybody fixed it by the time I walked around, but I saw some people have 3 and others have -3. What's the correct answer? Both. You need both, and you could see it if you factored it out, or if you set it equal to 0 and just remembered what happens when you take the square root in an equation, but you do need both of those. And as you see it on your graphing calculator, you will see numbers approaching vertical lines in 2 places, at 3 and then also at the -3. And then you can see how it happens. It goes here, and then it also comes up through here, something like this, and then also in this way as well. Okay, so the goal of the first page of the notes was to see the vertical asymptotes. Any questions on the first page? Okay, let's flip it to the next side then. The second page is going to have a little bit different of a goal, but I'm going to see if we can develop it based off of this first question. So the first question says, for the next example, what do you expect to happen at x equals -1? So what would we expect to happen based off of what we just learned? You would expect an error. How would it look on the graph, do you think? I mean, based off of what we just learned, I would envision a vertical asymptote, and in some way the numbers approaching that. This would be my vision. But let's go ahead and let's take it to the calculator and see what actually happens. So if I go to y equals and I do x squared minus 1 over x plus 1, and I graph it, I find that my vision is very poor. What happens on the actual graph? What did you say? It's just a line. It's just a straight line, and it kind of looks like this. It kind of looks like it has a y-intercept at, what, -1? Yeah. What's the slope look like? +1. It looks like it just goes kind of like this. Okay, hold on a second. Should there be an error at -1? There should be, because we can't have a denominator equal to 0. So let's look at the table and see, is there still an error at -1? So go to your table, press second graph to get to your table, and oh, I'm going to have to change my table set. I'm still on the last one. So I'm going to change my table. I'll press second window to start at 0 and go up by 1s. And now I'll look at my table and see, okay, what happens at, oh no, I'd have to start at a different place. Sorry, I have to start at like -2 because I'm trying to see what happens at -1. So what does it show in your table at -1? So if I like look at this as my table, what happened at -1? It's an error. Notice that doesn't really show up in your graph. What's actually happening in your calculator, I'm going to erase this part, is you actually have a little tiny hole at that point. A little tiny hole. And then everything else just continues in the form of a line. Now, we obviously have to figure out, why did this happen? Why was this function different than the previous ones we just looked at? What do you think it is about the actual function that created a hole? What do you think, Linda? You can simplify? Excellent. If I look at x squared minus 1, this is really x plus 1, x minus 1. And then keeping in line with my denominator, Linda's exactly right. She said we can simplify. Guys, what can we simplify? The x plus 1's. And what are we left with? We're just left with the linear equation, the line x minus 1. Now, how do you think I can determine? So obviously my y-intercept would be -1. That would be my y-intercept. My slope is equal to 1. And that's why I can see it happening on the graph. It goes at -1, I go up 1, right 1, up 1, right 1. But how do you think I can find the location of the hole? Because I have a circle here, and it's in a specific location on the xy plane. What do you think I could do to determine where will the hole be located? Just plug in -1 into what? Into the reduced function. We actually plug it in to the x minus 1. So if I plug in -1, then I'd have -1 minus 1, which gives me -2. Notice that this point on my graph is at -1, -2. Okay, so let's go ahead and let's answer these questions here. Look at the table. Is there still an error when x equals -1? Yes, we answered that. How is the function different than all other functions we have looked at in this section? I like what Linda said. The function can be simplified. The function can be simplified. So that is going to confirm what you would need to know about a hole. A hole will occur whenever a factor cancels. Or you could use Linda's term, whenever the function can be simplified. So a hole will occur whenever a factor cancels. Or you can think function can be simplified. And then how do you find the y-coordinate of the hole? We did that above. You plug it into, why can't you plug it into the original function? Why do I say reduced function? You can't put -1 in the denominator. Excellent. You'll get an error. So that's why you have to plug it into the reduced function. Excellent. So how do you find the y-coordinate of the hole? You plug into reduced function. Okay, so let's bring what you've just learned together. Which of the following equations has a hole? Which of the following have a vertical asymptote? And which of the following have both? Jeremiah.
I had a question.
Yeah, please.
How do you so but if you plug in -1, wouldn't it just be 0 on the top and 0 on the bottom?
If ever you have 0 on the bottom, it's not a mathematical value. 0 on the bottom is always undefined. So whenever you're going to have a 0 on the bottom, it's a problem. If you're looking at a graph, it's a problem as a vertical asymptote or a hole. If it's a number, it's just not a number value. So I understand what you're saying. Yeah, you would think 0 over 0 would give you 0, but it's because the 0's in the denominator that you can't envision that. Good question. All right, guys, so why don't you answer this with your partner? If you find any holes, find the location of the hole, and try these 3 together. Let's see, I'll throw out some Starburst. I feel like we need a little sugar to wake us up this morning. So, raise your hand for Starburst for you and your partner. If you could tell me, what'd you guys get for the first one? Keenan. It's a hole. Awesome. You did that because you factored the top and the bottom, and you noticed that something canceled. Did you find where the hole was located? So it would be at -2 and plug it into the reduced form. So you're left with x minus 2. So -2. What's -2 minus 2? -4. There we go. I didn't know if you said that. It was hard to hear you. So, yes, -2, -4 would be our hole. Nice job, Keenan and Garrett. Okay, can someone raise their hand and tell me the second one? Whoa, sorry. What would be the second one? Linda.
Oh, it would be a vertical asymptote.
Yes, where? Yes, at x equals -2. Nice job, Maggie and Linda. And then this last one, maybe the toughest. Raise your hand and tell me what would be the answers to this function. Does it have both? Where would they be located? Charlie? Awesome. Nice. So did you factor the top to x plus 2, x plus 3, and the bottom to x plus 2, x plus 4? Nice. So you found the vertical asymptote at x equals -4. Love it. And what did you say the hole was at? -2. And then what would the y value be? Well, if you plug it into the original, it might look like 0. But remember, we got to plug it into what's been left over, the reduced. So it would be -2 plus 3 over -2 plus 4. I don't know, what does that simplify to? 1/2. Perfect. All right, good. Any questions about vertical asymptotes or holes? Vince?
Where do you get -2?
So it's the -2 comes from the value that would make 0 in the denominator. So like if I have x plus 2, -2 would cause a 0 in the denominator. So that's where there's going to be a problem. Specifically, what type of problem will it be? Because it reduced, it will be a hole. If it didn't reduce, it would be a vertical asymptote. Good question. All right, any other questions? We move forward. All right, let's keep going here. So let's see if we can bring some of this stuff together. Can you create the equation and graph that has the basic shape of y equals x squared, but has a hole at the location 2, 4? So I'll give you a second to think about this with your partner. Give another opportunity for Starburst. Why don't you guys try this with your partner, and then we'll come together and discuss, see what you have. Through. Okay, Charlie, I saw you first. How did you get it?
Well, I had x squared multiplied by x minus 2 over x minus 2.
Okay, how did you know there was an x minus 2 and an... Yes, because I have an x value equal to 2 as a whole, therefore I know x minus 2 has been in the numerator and the denominator. Okay, and then what did you have also? He had the x squared because this is the shape that we need to maintain. So how does that work? The x minus 2's cancel, so I know that I have a hole. If I'm thinking about xy, I have a hole at the value of 2. And then how can I check to see if it's at 2, 4? Well, I plug it into what's left. So 2 squared gives me that hole at 2, 4. So now if we graph this, then I think about my basic x squared shape, 0, 0, 1, 1, -1, 1. I could look at 2, 4 and 2, -4. What's the only thing I have to adjust? I need that hole. So at 2, 4, I'm going to kind of erase that part. I need a hole there at 2, 4. So I can go ahead and connect. And there would be the shape that matches my equation. Nice job, Charlie and Jaden. Any questions about that? Okay, last but not least, we're going to take a look at the horizontal asymptote. So you guys saw that, well, sometimes the graphs seem to have a horizontal line that they hit. To help us understand horizontal asymptotes, we're just going to take a look at a few examples first that just will help solidify it. So first of all, horizontal asymptotes tell the y values for which the graph will approach when the x values get infinitely large or infinitely small. So to determine the horizontal asymptotes, we are going to examine the question, what value does the fraction approach as we let the x values grow to infinity? So remember, rational functions are just functions that are fractions. So if I'm looking at the actual y value, the value that comes out of the fraction, I want to see, well, what happens as I get infinitely large? So take a look at these fractions. Tell if the following sets of fractions are getting larger or smaller in value. So this first one, yep, these are getting smaller. So notice that the numerator is a tiny number, and then the denominator is a bigger number. And as the denominator gets bigger and bigger and bigger, it gets infinitely smaller. How about the next set of numbers? The numerators are bigger, the denominators are smaller, so what's happening to, it's getting larger. Some people might say it's going to infinity as it goes on forever and ever. Now take a look at these values. If I have 4 over 6, 4 over 9, 4 over 10, 4 over 11, 4 over 12, 4 over 13, 4 over 15, 4 over 16. Imagine doing 4 over 1,000. What are these numbers heading towards? They're heading towards, what did you say? What's 4 over 1,000? Let me look on my calculator. 0.004. So 4 over like a billion would be however, what is it, 6 zeros and then 4? So what are they all approaching? They're all approaching 0. This is what you want to think of as you're looking at horizontal asymptote. What are the value of the fractions approaching? So let's take a look at the 3 cases that could arise. Case number 1, if the degree of the numerator is bigger than the degree of the denominator. So consider what is happening to the value of the fraction as x gets huge. So what's happening as I have x squared over just an x to the first? I have a larger number over a tiny number. And as this goes to infinity, as x gets bigger and bigger and bigger, the numerator is going to become infinitely large, and the denominator is going to get less. It's not going to be as large as the numerator. So what's going to happen to the value of the fraction? It's going to, what happened here? It's going to approach infinity. It's going to get larger. It's going to approach infinity. That arrow, it means approach. So if you're like, what is she doing with the arrow? It just means approach. So the value of the function, the y values, are going to approach infinity. Okay, case number 2. What if the degree of the numerator is less than the degree of the denominator? Consider what is happening to the value of the fraction as x gets huge. So if I have a smaller number, so the fraction is tiny over bigger, it gets bigger and bigger and bigger in the denominator, what's going to happen to the value of that fraction? It's going to get smaller, and specifically it's going to approach 0. Last but not least, what if the degree of the numerator is equal to the degree of the denominator? Well, if we look at the actual fraction, consider what is happening to the value of the fraction as x gets huge. So let's just plug in a number. Example, somebody give me a really big number. 2 is not big. 85 is big. 1,000,000? I like that one. Example, let's say that x is equal to 1,000,000. Let's see what happens to the value of this fraction. It would equal 5 plus 2,000,000 over 1 plus 1,000,000. So if I actually did this on my calculator and I have 2,000,005 over 1,000,001, what does it show it's equal to on your calculator? 2,000,005 over 1,000,000. I might have not put enough zeros. What is it getting close to? What should it get close to, Charlie? Yeah, it's going to be approximately 2. Why is it doing that? Because as the x's get really, really big, so if you think about this on a graph, as x approaches infinity, these little tiny numbers don't matter. So what's going to happen is that the horizontal asymptote, it's going to approach the values of 2. Graph this on your calculator to help you visualize this. So go to y equals, and let's do 5 plus 2x over 1 plus, or what is that? Yeah, 1 plus x. if I graph this, what you're seeing visually is you have a horizontal asymptote at 2. So we know that we have a vertical asymptote at -1 because that was in my denominator. So at -1 I have that vertical asymptote. But now I can see that the horizontal asymptote, as x approaches the end of the graph, as it gets infinitely small or infinitely large, the numbers are approaching a horizontal asymptote at 2. So this is what you should be seeing on your calculator. Okay, these are the 3 cases of how to determine a horizontal asymptote. So to find the horizontal asymptote, you have 3 cases. Case 1 is what you saw at the top of the page. If the degree of the numerator is greater than the degree of the denominator, just like the first example. So if you wanted to put an example, you could just recopy that one, x squared minus 4 over x plus 1. Then you will have a horizontal asymptote, I'm going to call that HA, at nothing, because it's going to approach infinity. Because the x and y values are just going to get larger and larger and larger. So there's not going to be any number they're approaching. Case 2 is what you saw in the second example. If the degree of the numerator is less than the denominator, which looks like x minus 4 over x cubed, what is that, plus 6? Then you're going to have a horizontal asymptote at y equals 0, because the value of the y's are now approaching 0. And lastly, case number 3, if the degree of the numerator equals the degree of the denominator, just like that last example we had, 5 plus 2x over 1 plus x, then you're going to have a horizontal asymptote at the ratio of the leading coefficients. I know that's big words. At the ratio of the leading coefficients. So you can see here the degree of x and the degree of x are the same, and that's why we had a horizontal asymptote at 2 over 1. So for this specific example, the horizontal asymptote would be at 2 over 1. Okay, I know that's a lot, but you need to know those 3 things in order to graph rational functions. So let's put it together. Let's start with the horizontal asymptote, because that's the most recent learned. So it says find the vertical and horizontal asymptote and then sketch the graph. So let's start with the horizontal asymptote. Look at the function given to you. How do the degree of the numerator and the denominator compare? They're equal. Okay, so degree of numerator equals denominator. So what's my horizontal asymptote going to be at? Good, 1 over 1, which just simplifies to 1. So the horizontal asymptote is y equals 1. So that's what I can do to start graphing. Create your x and y axis, x, y, and at the horizontal asymptote, so at the value of 1, I know that my numbers are going to approach this horizontal line but never reach it. Then looking at the vertical asymptote, let's give ourselves a reminder. How do you find the vertical asymptotes? You guys remember from the first page? Yeah, where the denominator equals 0. So where would the denominator equal 0 here? Now make sure you list it as x equals because it's not a whole. How do I know it's not a whole? You can't reduce it. Good. So does this problem have any holes? No. Did I, on your notes, give you an option for a holes? Yeah, I wanted to, just because I want you to make sure you know you always find the holes first, if they're there. But for these two functions, there's no holes. So there's no hole because nothing reduced. Okay, the next thing, the only other thing I have to do is make a table to determine what's the behavior next to these asymptotes. And you will always be asked to find the x and the y-intercept just because those are important pieces of the graph. So how do we find the x-intercept? It's where what? Y equals 0. So I'm just going to take and set the function equal to 0, and I have x minus 5 over x plus 3. Yes, it's at 5. Now, if you're like, how do you know it's at 5? You could technically multiply the denominator out. If you just don't like eliminating things from your equation, you can see how it eliminates. X plus 3 times 0 is 0. So if 0 equals x minus 5, then x is going to equal 5. So my x-intercept is going to be at 5, 0. So I'm going to go 1, 2, 3, 4, 5, 0. How do you find your y-intercept? Yep, where x is equal to 0. So my y is going to equal 0 minus 5 over 0 plus 3. What does that become? Negative 1 2/3. So my y-intercept is at 0, negative 1.6. So I go 0, negative 1.6. Now that I have 2 points to the right of my vertical asymptote, I know how the shape of this graph will look, at least to the right-hand part of the graph. I know that it's going to go through those points, because your graph always goes through points, and it approaches but never reaches your asymptotes. Now, how can I figure out, because you guys know based off of what we've done on the calculator, how can I figure out what happens over here? I don't know if it's always reflective. It's a good way to think about it, but it's not always reflective. Probably the best way is just to plug in a number into your table. So what would you plug in to determine the behavior over here? Maybe like an x value of negative 4. See what happens. So if I plug in negative 4, I would have negative 4 minus 5, which would give me negative 9 over negative 4 plus 3, which is negative 1. So negative 9 over negative 1 would give me 9. And I can go negative 4, 9. I know it's up here. And now I know where the shape of the graph will look like on this side. So how do you find horizontal asymptotes? Again, it comes from the degree of the numerator versus the denominator. Okay, I'd like you with your partner to just fill in the blanks. Fill in the vertical asymptote, the horizontal asymptote, the x and the y-intercept. This is the good stuff.
Hey, here we go.
Mark, look back at the boxes and say, what do I need to remember? And then put it together. Hey guys, one thing I do want to point out to you, your horizontal asymptote, that tells the end behavior of the graph. So you see how you have an x and a y-intercept at 0, 0, even though that's on the location of the asymptote? That's because the y values at the end is when x approaches negative infinity and when x approaches infinity. So it does cross in the middle here. Now, how can we determine the other parts of the graph? You just really need to use a table and plug in numbers to the left and to the right of the vertical asymptotes. So if I look at this vertical asymptote at negative 2 and 2, I'm going to plug in a number like negative 3 into my function. So I would have negative 3 over 4 minus negative 3 squared would give me negative 3 over 4 minus 9, which is negative 5. So I have -3 3/5. What's 3/5? That's like 0.6. So I have this. So now I know this shape because at the end of the graph, it's not going to touch the horizontal asymptote. And it's always going to approach the vertical asymptote, but never touch that as well. I have to figure out what's going on in the middle. So I would plug in a value like -1. At -1, I have -1/4 minus -1 squared. That's -1/3. So I have -1, -1/3. So I see that this graph is going to go through and approach here. I would want to plug in a value like 1, which you would plug that in and you would get 1/3. So you can see the kind of middle shape of the graph. And then finally you plug in the number 3 to the right of the vertical asymptote, and you're going to get 3/-5. 3/4 minus 9. So we have 3 and then -3/5 down here. So the graph should be down here, approaching that way.
Basically, you just plug in numbers.
Plug in numbers and then just use your asymptotes to guide the shape of your graph. You can check it, and I encourage you to check it on your calculator for tonight's homework. You only have like 5 questions, but you can see that these questions are just loaded with material. But I'm going to check to make sure I didn't make any errors in my table. And no, that's